So our first one is Armands Strikis, who is going to be talking about how quantum computing is scalable on a planar array of qubits with fabrication defects. Take it away.
All right, thank you very much. Yeah, perfect. So today I'm going to tell you about my recent work regarding the scalability of planar architecture quantum computing in the presence of fabrication defects. That was work jointly done with Benjamin Brown at that time at University of Sydney and Simon Benjamin from Oxford University. So the outline of the talk is as such. First of all, I will try to explain to you why fabrication errors or defects are generally detrimental for planar quantum computation. I will propose our solution. I will show you how our solution yields to theoretical guarantees. And finally, I will explain and show some new work in progress and also just conclude the talk. The majority of the talk will be focused on the problem statement because I feel like to fully appreciate the theoretical results that we have derived, one really needs to understand what was the problem in the first place. I think there's not a lot of motivation needed why planar architecture is quite promising. These are one of the latest efforts from Google and IBM, so on the superconducting qubits. These are planar architectures. And whenever we talk about planar architectures and scalability, the first thing that comes to mind is error correction and surface code. So I think most of you have seen this figure on the right-hand side from Austin Fowler, one of the famous figures on surface code. So the yellow and the green bits of that figure represent parity for checks, the stabilizers that check the data qubits around them, the white bits. And these are the two quantum circuits that extract this information out of the nearby bits. So this is like a topologically local two-dimensional code. And what we will do, or what I will do in this presentation, I will use a slightly simpler or visually clear representation of the surface code, which is this grid with qubits on the edges as some of the black dots are presented there. The stabilizers being either plaquettes for Z stabilizer, which acts on the 4 nearby edges or 4 nearby data qubits. And similarly for the X stabilizer, which is a star operator, and then just it's a vertex operator and acts on the nearby qubits around the vertex. So really quick recap on how surface code works in terms of quantum error correction. Because it's a CSS code, we can treat X errors and Z errors separately. And here are some of the X errors shown, where they are represented as error strings on data qubits. And as you can see, that whenever a data qubit goes under an X error, the nearby or the stabilizers on the ends of the error strings light up. So these are the ZS stabilizers that detect X errors. And it's quite important in this context that these are the ends of error strings. So this is a very specific feature for the two-dimensional architecture of the code. So now, what happens when we have some fabrication error as such, where, for example, one of the stabilizers is either missing or faulty, or any kind of variation where the stabilizer is not functioning as necessary? We can see that now we may not. So this is represented by the F, letter F, and we can see that the qubits on the right of this faulty stabilizer, the errors on these qubits are not detected anymore. And essentially what it really means in terms of in coding theory is that these errors map the state from the code space to the code space. It's not detected, and we end up with a logical error. And this logical error is essentially also represented by the crossing of the Z logical operator shown here on the left. And overall, what really that leads to is that we have now reduced the code distance or the protection that we have on the qubits massively. Obviously, we can use the right-hand side of the code, which is slightly like bigger, but if we have a finite number of these fabrication defects, then you can see that there's going to be some kind of a almost characteristic length of a distance that we can obtain using this circuit code with fabrication defects. I mean, generally, there is also the one could even think about it as in terms of quantum computation with fabrication defects or specific defects. So this is defect-based quantum computation, where you on purpose put on these defects and essentially start forming more and more logical qubits. But whenever we are thinking about scalability of a single logical qubit, we want to scale it to arbitrary low logical error rate. Then and since we can't place the fabrication defects ourselves, but they are just randomly assigned, then that is quite a problem. So a solution for this was proposed first in 2009 by Thomas Stace, Sean Barrett, and Andrew Doherty, where they proposed to enclose any kind of fabrication defect, as it's represented on the right figure as this white hole, in super stabilizers. So this is a construction where we turn off some of the CNOT gates that link the super stabilizers to data qubits to form these kind of gauge operators around of the hole. So there's two different kinds of gauge operators. There are X and Z gauge operators, where X are represented by alpha, beta, and gamma, and Z are represented by A, B, and C. And generally, they do not commute with each other. As you can see, beta and C, for example, they share a single data qubit, so they are not commuting gauge operators. So we may not measure them at the same time, but what we can see is that the product of all of these A, B, and C, and a product of A, B, and C, and a product of alpha, beta, and gamma, they commute themselves with each other. And so we can use the invariant of the product or the super stabilizer to actually start detecting if the error strings, the ends of the error strings are terminating at this boundary, this hole, essentially. There's a slightly different representation on the left that we use in our paper, which just makes things a little bit clearer for analysis purposes, where we essentially form super stabilizers as squares around fabrication defects. Again, you can see that, for example, Z1 and X1 gauge operators, they themselves do not commute, but the product of all of them do commute with each other. So we can measure one and then measure the other one sequentially. Now, what's the problem with that? It seems like that's a solved case, and so on and so on, but it's not quite, because again, we are talking about scalability, we're talking about the asymptotic regime. And as we're going to scale up our lattice of the surface code to bigger and bigger sizes, we expect that we will not be able to enclose every single fabrication defect individually, because they will start clustering together into forming bigger patches of fabrication defects, as shown in the right bottom corner of this grid. And what does that mean is that once we start trying to enclose the fabrication defect in this kind of super stabilizer formalism, each individual gauge operator that the super stabilizer consists of has some finite chance of measurement error, and that leads that this full super stabilizer has quite a large measurement error in the end, once we scale to bigger sizes where the clusters are way, way bigger. And we have bigger clusters, we have more of them as we scale up. We essentially have some characteristic length between the clusters. The clusters themselves are super noisy. They act almost like holes because we cannot extract any information. Their measurement error rates 10 to 50%. And in then what we expect to happen is that the threshold as the infinite scalability to arbitrarily low logical error rates just vanishes. So in 2017, oh yeah, so this figure is taken from this other paper from 2017, which is like kind of continuation of this this topic. So also in this paper from 2017 and some other papers, the open problem was posed, asking, well, if we have this finite rate of fabrication defects, can we actually obtain a threshold below which we have like this exponential suppression of the logical error rate? And this is the problem that we are trying to tackle or tackled in our paper. And our solution consists of a couple of ideas. The first idea is that we will fix the gauge of the superstabilizer for longer than just a single round. So in the stasis method, as previously, we would measure the superstabilizer by measuring prospective gauge operators, let's say in X gauge operators. So we measure the X superstabilizer, then we switch to Z superstabilizer, then we switch to X, and so we alternate every single measurement round. We propose to keep measuring one type of superstabilizer for longer. Unfortunately, this figure is not fully rendered, and some of the other figures will also not be. I should have checked on Microsoft that the presentation also looks that good. But the one on the right, that's PNG format, so that's fine. And it should look like all the figures that will be also presented later should look like the one on the right hand side, or close to that. So here, what I'm representing are these little squares are essentially these gauge operators themselves. And one round of measurement would be 1 perimeter around like a circle around it, and that is representing the super stabilizer. And as you can see, we measure greens for multiple rounds, and then we switch to blues, and then we switch to greens again. And what that allows us to do is to find out what the gauge operator values themselves are, because whenever we switch from one gauge to another gauge, we completely randomize these values because these are non-commuting operators. But if we just measure in the Z gauge for multiple rounds, we sacrifice the fact that we don't know for a long time what the X superstabilizer value is, because we are not measuring it for a long time. But we can infer the values of the gauge operators themselves. So in this sense, we are kind of homogenizing the space and time together. So very quick recap, what happens, for example, if an X error, so these are represented by these red strings, terminates at a smooth X boundary. So that is not detected the time while we are measuring the X stabilizer, because it just does not detect X errors. But what we can compare is that the stabilizer just before the shell, so these things we call shells, just before the shell of the X shell, the stabilizer is in +1 eigenvalue, and then the stabilizer is -1 eigenvalue. And by comparing these two values, we can infer that some error has terminated at the smooth boundary in the time while we were not measuring the Z superstabilizer. So now the second idea was that to make it, again, more homogeneous between space and time, we will try to gauge fix proportional to the size of the cluster. So the bigger cluster is enclosed by the superstabilizer, the longer we will measure it in some specific gauge before we switch to the other gauge. I'll imagine that there's colors, it's green and blue alternating, and same when we have more of these fabrication errors. So some of them are smaller, some of them are bigger. I'm just trying to show that the bigger ones are alternating less frequent, because essentially there are more gauge operators, there are more the combined noise is greater, so we want to keep measuring the gauge operators themselves to better infer what the values of them are. So how do errors look like? So again, the errors are detected at the ends of we detect stabilizing measurements or syndrome events at the ends of the error strings. And what's very specific about this construction is that some error string can terminate at a shell And if it leaves the shell before we switch to the other gauge, it will not be detected at that shell, but somewhere else. So for example, in this, the bigger shell, we can see the string enters in one place of the shell, and then it exits the other shell side of the shell, and it's not detected at the shell that our string has gone through. So before I get to the threshold theorem itself, it might be good to characterize the fabrication errors. And this is what we do. We do it with some kind of clustering algorithm, where we also say, well, obviously, if the whole chip is broken, you will not be able to scale it, or like you do any kind of computation. If you produce any kind of chip and someone smacks a hammer on it, and then you will not be able to use it for computation. So there's essentially some kind of a limit how many fabrication defects we can actually tolerate. So what we do is we use a clustering algorithm from that is also presented in Bravi and Ha. And what it does, it clusters fabrication defects into different levels, where each level is a linear size of at most q to the I for some constant, which our construction requires to be at least 9. And it also does is that it says that every I level cluster is at least distance q to the I from any other cluster of that size, of that level or larger. And that gives us enough properties to actually start using some very interesting analysis. We say that the lattice is operable if the largest cluster is less than half the lattice size. Sorry, if the largest cluster, the cluster is less than half the lattice size. And that is achieved with exponential probability with respect to the size of the system. If the fabrication defect rate is below some kind of threshold. So there's like some kind of a fabrication defect rate threshold already. So this is our main theorem of the paper. So let's suppose that the lattice is operable. So the biggest cluster is only at most half of the lattice size. Then there exists a phenomenological error rate threshold. So this is errors that describe the qubit bit flip, phase flip, and also measurement error rates. Such that if we scale up the system to bigger and bigger sizes, we can exponentially reduce the logical error rate, and that scales with the distance exponentially, and as long as the error rates are below this threshold. Such a statement would be very difficult to come by in the previous case, where we alternate stabilizers every single round, and we have also some not foolproof, but some analytical hints on why this is not possible. So a very short outline of the proof. For the full mathematical proof, please refer to the paper. But what we do is we count every single error configuration that can lead to logical error. And that is the presence of these shells. Again, so these are essentially the logical failure forms. Once after decoding, we end up with some logical strings that span the lattice. So they can enter one of the shells, and then they can exit the same shell from a slightly different direction, as I indicated previously. And that immediately makes way more kind of pathways that a single string can percolate through the lattice. And then we also weight each of the shells by each of the paths by its probability of occurrence. So obviously these are error paths. So that means that every single qubit along this path has suffered some kind of error. So, and we can do some overcounting arguments where we essentially try to, because we don't want to consider every single configuration of these shells on the lattice, we try to consider some really worst case scenarios of the configurations of the shells along every single path. Actually, we consider such worst case scenarios that they're way worse than practically possible. And what we end up with is with a threshold that is represented or written as 1 over rho squared, where rho is this crazy number that only depends on Q. And from the clustering algorithm, we know that Q needs to be at least 9. So if you use clustering algorithm with that Q number, we end up with a threshold of something like 10 to the minus 27, which is very, very, very low, but that is a lower bound threshold, and we do not expect it to be anywhere close to that. So what we really wanted to show is that it's non-zero. Also, this scheme, I feel, is I have good reasons to believe is also applicable to other time-correlated errors, such as cosmic rays. So these manifest almost very similar to these fabrication defects, where for some time the lattice experiences a lot of noise, or like there's also essentially almost a hole in some region. So we can enclose them into the shell formalism for a while and then stop it. That's something that also some people are already investigating. And some of the further work. So obviously, all of this, what I just described, is asymptotic regime. So this is to deal with scalability. But now in practical regime, there's some more work and progress by my colleagues Adam Siegel and Tom Flatters, where they just consider finite scale surface code, and they do numerical simulations of what happens when we have this fabrication defect in the middle of it. And they scale the fabrication defect, and they see how our scheme of shells compared to the previous scheme, stasis scheme, where we alternate super stabilizers every round. So you can see already the sizes of d equals 7, where d is essentially this kind of diameter of the fabrication defect. Our method, which is a solid line, already starts outperforming in terms of the logical error rate. It starts outperforming the method where we alternate super stabilizers every single round. So the main takeaway from this talk and from the paper itself, what we wanted to really present is not so much the method of how to deal with these fabrication defects, but more of giving you a guarantee that fabrication defects are not fundamentally detrimental to scalability of planar architectures. And that's exactly why we wanted to find this threshold to be non-zero, such that there is definitely some kind of a scheme that allows you to scale the architecture all the way arbitrarily large and obtain arbitrarily low logical error rate, but exponentially fast. Some of the future directions is continue work in the practical setting. Again, the lower bound threshold that we found is not something that we would expect. We actually expect the thresholds to be very comparable to the previous thresholds found from a stasis method, for example. Explore other time-correlated errors. Again, these are, for example, the cosmic rays, but there are also some other more exotic ones. Generalized to other planar codes. We took a surface code as like one example, but very similar arguments also would apply to color codes, for example. And in general, I feel that it would be very beneficial to start using more and more of these time degree, the time degree freedom for more of the benefits of some of the error correcting code architectures and so on. Yeah, thank you for attention, and thank you for listening.
Thank you very much. Do we have any questions?
Very quick one. So the way I was understanding it from talking, maybe I missed something, is that you're sort of aware of these fabrication defects before you actually.
Yeah. So that's an assumption that's made that
So with cosmic rays, I imagine that would work because you would have to be aware that.
Can you just repeat the question?
So the question was, the assumption is that we are aware of where the fabrication defects occur. How about the cosmic rays? So the answer is yes. It's not as easy now to detect the cosmic ray events as well, but there are some kind of essentially algorithms that would detect a very huge burst of lots of syndrome events in some region, and that would give you some kind of hint that a cosmic ray has happened there, and we can start enclosing. So then also that's why, for example, in this slide, there is some kind of a time between T1 and T2 So this is the detection time to actually find out, oh yeah, so there's actually a really big number of errors happening in this one region. This is when we start enclosing it at T2. Thanks.
Hello, thanks for the nice talk. We just back to the theory statement. So I was kind of expecting to see somewhere the density of fabrication errors would be.
Yeah, so the whole theorem is based on that the lattice is operable. So that means that the biggest cluster of the fabrication error cluster is bounded by this d/2. And once that is satisfied, and we are using this kind of a chunk clustering algorithm, then the threshold statement follows.
And
The threshold of around 10 to the -7. So
Lower bounds.
Yeah, okay, fine. The same chunk clustering algorithm used to be code, if I recall, lattices with no defects, and they also came up with a really small proven threshold, right?
Yeah,
Okay,
so that was something 10 to the -6 or so.
So there was 10 to the -6, yours is 10 to the -7.
So these are slightly different thresholds. So the 10 to the -6 is the fabrication defect rate threshold.
Okay.
So this is essentially below which we can expect that the largest cluster is going to be only half the size of the lattice, while the other threshold is the qubit phenomenological error rate threshold. So you have like these two different thresholds. One is for the qubit error rates and one is for fabrication error rates.
Okay.
So the one that they've derived was for their qubit error rates, but we use it for the fabrication defect rates. And the one we derive is now for the qubit error rates. And that's that. It's so small just because we just simplified the analysis in multiple steps. Like there's a lot of simplification going on, but we expect it in more practical regime it to be something like 10 to the -4 or so.
okay, let's thank Armand again.